Lesson 9 builds on optimizations from last day. Today we're going to focus on exploring solutions and solution regions. Again, also called feasible regions. What answers are feasible? Feasible is the solution region for a system of linear inequalities that is modeling an optimization problem. So feasible generally means makes sense. So here's the pop example from last day, the cola and the Dr. Pepper. And I'm going to give you a minute to pause the video and write down these inequalities from last day. Then we're going to graph them to try to determine where is the feasible region and what does it look like. Okay, so let's go ahead and write the objective function. Remember what the objective function is? Look in your notes from last day. So let's fill in the objective function. And this one, it's a silly one. It's the number of burps. As it says in the story, you get 3 burps for every liter of Coke, and you get 2 burps for every Dr. Pepper. So we're trying to maximize number of burps. Fun family. Okay, let's go ahead and draw all these functions. So I'm going to do the x plus y is less than or equal to 12 first. Again, less than or equal to is a solid line, and you could graph it however you want, but I'm going to find those x and y intercepts, or I'm simply going to make up some numbers that add up to 12. And when you draw that, we get this line here. Again, I apologize, but I can't draw a line with a ruler on this. So there's our big one. Then we're going to draw the y. The y is greater than or equal to 6. Well, again, if you plotted that line, that would be y equals 0x plus 6. 0 slope, y-intercept of 6, and that would just be a flat line that would look like that. And given that y is going to be greater than 6, it's going to be up there. Similarly, given that x plus y is going to be less than 12, our answer is going to be that way. So I'm not going to shade everything this time because it'll look very, very messy. So I'm just going to put some arrows indicating above, below, or whatever. The other one is y is less than or equal to 12. Again, imagine the equation y equals 12. Y equals 0x plus 12, and a 0 slope and a 12 y-intercept would look like that. So right now, my solution has to be above 6, below 12, and to the left-hand side of that line. And finally, we'll do the x stuff in green. Now, we haven't talked about how to graph an x equals line, but an x equals line is a vertical line. So just like y equals is horizontal, x equals is vertical. So here's our x equals 3. And again, it's solid because it's greater than or equal to. So we're going to look at everything bigger than that. And again, x less than or equal to 12. So here's kind of the picture. We have 5 lines. And when you look at those 5 lines, you have to figure out where the answer is. And I'm going to highlight it. I'm just going to shade it right now. But as we're going to talk about in a sec, we really can't imagine this whole area is where it is. So that little area right there is above, below, right, left, and underneath. So there's our feasible region. So then feasible region, kind of. So again, remember what the feasible region is. It's the solution region. It's the possible answers. That's basically what it is. But given that x and y have to be whole numbers, no decimals, then it turns out that the feasible region is really just the nice coordinates, in the shaded region. Again, we cannot have a half a bottle, right? So in this one right here, it turns out that we actually have 10 possible answers. And underneath here, I'm going to do this really quickly, but I'm going to do a couple of examples, and then I'm just going to fill in. I'm going to fill in the blanks. So again, I'm just going to pick the coordinates off this and figure out the number of burps that would happen if you had 3 bottles of this and 9 bottles of this, or whatever, whatever, whatever. So if I labeled them, this would be my first one. That's the first point I'm going to use, and that's 3 comma 9. So using 3 comma 9, the number of burps would be equal to 3 times 3 plus 2 times 9. And that would represent 27 burps if you bought 3 cola and 9 Dr. Peppers. If you bought the one below, or if you did the one below it, 3 and 8, the burps would be, well, 3 colas and 8 Dr. Peppers, and it would be less. And I'll do, so that would have been point number 2 right here, and point number 3 would be 4 comma 8. So this is the last one I'm going to do, and I'm just going to fill in the rest. So B is equal to 3 times 4 plus 2 times 8, and that would be 28 burps. So I'm just gonna write the coordinates and tell you the burps for the rest. So 3 comma 7 is going to be 23 burps. 4 comma 7 is going to be 26 burps. 5 comma 7 is 29 burps. 3 comma 6 is 21 burps. 4 comma 6 is 24 burps. 5 comma 6 is 27 burps. And finally, 6 comma 6 would be 30 burps. So there's the minimum right there. And if the question was, how much should you buy to minimize burping? Well, it should be that one. If I ask you the question, what should he buy to maximize burping? Well, that one would be that one there. And that point, that green point, 6 comma 6, is that one right there. So again, we've talked about the inequalities. We know how to graph inequalities. We talked about the objective function. It's a little bit tricky to figure out, but if you think common sense, we should be able to do it. And now we're talking about the feasible region, where the answers are going to be. And again, it depends on the kind of numbers that we figure out. Okay, let's look at one more example. So again, it's Buffy the farmer again. It's where she was planting corn and beans. And again, I'm just going to write the inequalities in from last day. You have them in your notes. So here's the corn stuff. Remember, X was corn and Y was beans. And here was our inequality, how much she could plant in total. Now in this one right here, we'll write our objective function, the thing that we want to maximize or minimize. And what we want to do is we want to maximize profit. So profit is going to equal the profit she can make off her corn and the profit she can make off her beans. And again, for every acre of corn, she makes $100, and for every acre of beans, she makes $150. So again, profit is equal to how much? Well, that's that amount of corn, but she makes $100 for every, and because we're adding, she has some beans and she makes that much on her beans. So this is the thing that we're going to try to solve. And in order to solve it pictorially, we have to draw the picture and look at, well, what could actually happen. So again, x plus y less than or equal to 8, we should be able to do that. So I'm just going to quickly imagine, I'm going to find the intercepts, however you want to graph it. And remember, I'm not going to shade because we're going to do a bunch of lines. It's going to get a bit messy. I'm just going to put arrows. Then we have to represent x is greater than 0. Well, remember, when we graph an x line, it's just a vertical line. So the x's are everything bigger than that, but everything less than that. And y greater than 0, well, y greater than 0 is the y equals 0 axis, and y is less than 6 is horizontal line. We talked about that earlier. So here's the feasible region right here. I'm going to highlight it. Here's our feasible region right here. It's everything below here to the underneath of that, to the left of that, and right here. So here's our feasible region. And given that these are all real numbers, again, you can plant decimals, right? 0.2 acres, whatever. Then this looks like a really tricky example, but I'm going to give you a hint. The maximum or minimums always occur at corners. So this looks like, wow, this is going to be a really hard problem to try to figure out. But if you look at your feasible region, it's going to turn out that the maxes and min, and if you don't believe me, check a bunch of points. But I'm just trying to give you a heads up. We actually, in order to solve this problem, we only have to figure out 5 points. So again, where's the feasible region? Where are the answers going to be? Well, again, I guess the true answer is all points of the shaded region including the border. But as I said, that's a lot of points. That's an infinite amount of points. We're just going to check all the corners for maximums. So that's a different question. Remember, if I'm asking you a question about where's the feasible region, that highlighted yellow area and all the lines on the outside is the feasible region. But if we're actually going to check for the right answer, then we only need to check the corners for the maximum. So again, I'm going to do this really quickly. I've labeled the points 1, 2, 3, 4, 5, and I'm going to list the coordinates of those points. Now remember, these coordinates represent corn and beans, and some of these are obviously you're going to chuck them right away. So all we're going to do is we're going to plug these numbers back into our objective function. So the first one is 0. Again, that would be ridiculous, right? And our second one probably isn't going to be the good one either, because we're only planting 6 of the 8 acres. So these two right here, that's when we're using all the land, and they're probably going to be the highest. So I'm just going to focus on these two from now on. And I'm going to have 100 times 2 plus 150 times 6. And that would be $1,100 profit. And this one right here would be 100 times 4 plus 150 times 4. And that would equal 1,000. So in this case right here, I'm not going to do the last one because it's only going to be 400 if you want to figure it out. But there we go. We're trying to figure out how much money we can make. And wow, who'd have thought math could actually help us? So Buffy, to answer a question, Buffy should plant 2 acres of corn and 6 acres of beans. And if she did that, she'd get a maximum profit of $1,100. Now, again, what we're going to do next class is actually go start to finish. But here's some key ideas, and this might be valuable next day. So again, the value of the objective function for a system of linear equations varies through the feasible region, but in a predictable way. So again, that really just says that You could look at numbers like 0, comma 0, and it's easy to see the answer. The optimum solution to the objective function are represented by points at intersections and boundaries of the feasible region. So again, that's the idea of you don't have to worry about every single point necessarily, just one, just a few, right? So again, that's when I said corners. Again, you can verify each optimal solution to make sure. That's why we figured out all the values. And the intersection of the boundaries called vertices or corners, and that's the word I like to use.